Assalamu alaikum and good morning, everyone. Today we are going to start with a new topic, still under the organic chemistry. And this next functional group that we're going to look at is carboxylic acid and esters. Carboxylic acids are compounds with the functional group COOH. Okay. When it comes to naming carboxylic acids, they have a system of naming in terms of suffix, which ends with oic acid. Okay, now the functional group of carboxylic acid will always be number 1. We say that COOH is always at the terminal or at the end of the chain. So when you have a carboxylic acid, automatically the carbon of the COOH will be carbon number 1, and the rest will follow. Carbon 1, carbon 2, and carbon 3 for propanoic acid. Okay. Here is an example of when you have 2 carboxylic acid group. There's one on the left, COOH, and another one on the right. This is called a dioic acid. The reason that it's called di is because there are 2 of them, and the oic acid is the standard naming system of the carboxylic acid. And since there are 2 carbons, it's ethane dioic acid. Okay, so just be careful, it's not ethane dioic acid, it's ethane dioic acid. So that's what I mean by carbon on COOH is always number 1, I believe. What does it say on the notes? Always number 1, yeah. Okay, moving on to the physical properties of carboxylic acid. We already know the bond polarity of the hydroxy group OH. Okay, since oxygen and hydrogen have very different electronegativity values, the oxygen will be slightly negative and the hydrogen will be slightly positive. This is because oxygen has a higher electronegativity than hydrogen. Now, there is another polar bond in this functional group COOH, which is the carbon and the oxygen. Oxygen versus carbon, we both know that oxygen will be slightly negative and carbon will be slightly positive for the same reason that the oxygen is more electronegative than the carbon. So seeing that there is more polar bonds in carboxylic acid, obviously the molecule will become a polar molecule. Again, it depends on how big your alkyl group is, your R group. R group usually represents an alkyl group. Now, hydrocarbons or alkyl groups are non-polar. So one side of the molecule is non-polar, or we call it hydrophobic. It is water hating, and the head, which is the COOH, is the polar head. Okay. Moving on to the next physical properties of carboxylic acid. When it comes to boiling point, again, since it falls under the organic molecules, they are naturally by default simple molecular structure. So when it comes to simple molecular structure, when we talk about their boiling point, really the only intermolecular force or the only bond that we are breaking or that we should be focusing on is the intermolecular forces, none of the strong chemical bond like the covalent bond. Okay, so we are only breaking the intermolecular forces. And as you all know, that there are 3 types of intermolecular forces. The first one is the IDID, instantaneous dipole, induced dipole, being the weakest intermolecular forces among the 3. And everything and anything that has electrons would by default have this IDID force. This IDID force is affected by, is controlled by 2 factors. One, the number of electrons, which is what you have here. The bigger the number of electrons, the stronger the ID force, therefore the higher the boiling point. Okay. The second factor is the surface area of contact. It depends on whether your molecule is a straight chain or branched chain. On top of the ID force that is present in the carboxylic acid, there is also the presence of hydrogen bond, for obvious reason, because of the COOH. Okay, and hydrogen bond is when you have a hydrogen that is directly directly attached to either F, O, or N. In this case, we have the OH of the COOH, okay, just like your alcohol. So carboxylic acids would have stronger intermolecular forces due to the presence of hydrogen bond. So it depends on what you are comparing with, okay? Then different factors come into play. So in this table, we've got 4 molecules: butane, which is an alkane; propanol, which is an aldehyde; propan-1-ol, which is an alcohol; and lastly, ethanoic acid, which is a carboxylic acid. So the MR values are quite similar. This suggests that the number of electrons are also similar, okay? So you can try to find the number of electrons of each of these molecule or formula. You will find out that they are not too far from each other. Okay, so MR and number of electrons are not the same. When you want to talk about the strength of the ID force, you should be talking about the number of electrons, not the MR. Why do we put the MR there? Just to show you that they are more or less, they have more or less the same number of electrons or mass. They're quite close to each other, okay? But the boiling point is very, very different. As you can see, butane has the lowest boiling point. So this suggests that the intermolecular force that is present in butane or alkanes are much weaker than ethanoic acid and propan-1-ol, for example. Okay, this is true because in butane there is only the ID force. Whenever you see this van der Waals, you can just change them to ID because the van der Waals is the old name for ID. Okay, so I try to avoid that. Propanol does not have okay, I'll cancel that as well. Doesn't have a hydrogen bond. It has ID and PD. Okay, so you notice this additional means on top of ID. Okay, on top of ID, there's a PD in propanol, and then for propan-1-ol, on top of ID, there's also hydrogen bonding. Now, you may argue that hydrogen bonding is actually an example of PD. Okay, so that's why it's not included here. So as you can imagine, the ones with the hydrogen bond have a higher or a stronger intermolecular forces, okay? As you can see, well, you don't have to explain why carboxylic acid have a higher boiling point than propan-1-ol, which is an alcohol, considering that they have the same hydrogen, but it just depends on the magnitude, okay? So don't worry about that. As long as you know why these two are much higher than the rest, and you can acknowledge the presence of hydrogen bond in alcohol and carboxylic acid, then you should be fine. Okay, moving on. Solubility, again, the idea of solubility is it depends on whether they can form hydrogen bond with water or not. Okay, so in this case, since carboxylic acids can form hydrogen bonds with itself, it can also form hydrogen bonds with water. Just like alcohols as well, the shorter chain alcohol are more soluble in water. Okay, this is because as the number of carbons or the number as the chain grows, the hydrophobic part of the molecule, the nonpolar part of the molecule dominates. Okay, and once the nonpolar part of the molecule dominates, it may look like the molecule is nonpolar. Remember, water is a polar molecule, therefore it only reacts with the polar head of carboxylic acid. Okay, so this is the same case as alcohol as well. Right, I am just going to label this as the nonpolar hydrocarbon chain. So in this case, there's only one CH3, obviously. So the bigger the size of this hydrocarbon chain, the more nonpolar the molecule becomes, okay? And then this area is the polar head. This part is hydrophilic, or we say water loving. Okay, there is a diagram on your notes that shows how hydrogen bonds are formed between a carboxylic acid and water molecules. Okay, so these are showing two different water molecules. The reason for this is because the water molecules are short, so you cannot just form a hydrogen bond with one water molecule. You may not. It's not necessary. Okay, so just a few things to point out when drawing hydrogen bond. You need to draw the dipoles, which are already there. The dipoles are between the slightly positive hydrogen that is attached to oxygen. Okay, so that's that. And then there's also a slightly negative charge on the oxygen. Okay, both of the oxygen. The only thing that's missing is the lone pair on oxygen there. Okay, likewise, the lone pair on water is also missing here. So please add that on. The general rule is that as the carbon chain increases, the solubility decreases. The reason is because carbon chain is non-polar. Okay, so we're talking about the solubility in water. Please add on to your heading solubility in water. It's a different story if we talk about solubility in organic reagents. So just remember, when it comes to solubility, polar loves polar and non-polar loves non-polar. Okay, moving on. This is another property of carboxylic acid. Now, the name carboxylic acid already suggests that it is an acid. Okay, so we talk about the acidity of carboxylic acid. Now, if I were to just go back to acids in general, okay, I think you are all familiar with HCl. So I'm just going to use HCl as an example. And we talk about dissociation. We talk about how acids are molecules that release hydrogen ions in solution. Okay, so what happens is that when HCl comes in contact with water or in aqueous form, it dissociates into H plus, which is the definition of acid, and whatever is left becomes your anion. Okay, H plus and Cl minus. So this is the dissociation or the ionization equation for a strong acid like HCl. This works for other acids as well, like nitric acid, sulfuric acid, phosphoric acid, and etc. Okay, but what if we are looking at an organic acid, a carboxylic acids? Okay, so carboxylic acids are weak acids. It dissociates partially. So this is a strong acid, and it it dissociates fully, completely dissociates. That's why you get a full one direction arrow. Is that right? Okay. Right. If we talk about carboxylic acids, so I'm going to use a specific example, which is ethanoic acid. Now, because it is an acid, it also undergoes dissociation. Now, the only difference is that it's being a weak acid. Okay, so dissociation of weak acid is usually represented by the reversible arrow. Okay, so this is for weak acid. Now, we're going to dissociate it the same way we've done for HCl. You have not covered this topic on dissociation of acids yet. That's why I'm going to break it down slowly for you. Okay, right. What happens? You will release H plus. So after you have released H plus, or break it down into H plus, you are left with the rest of the molecule that becomes an anion. Okay, so your anion is CH3 COO minus. So this is the dissociation of carboxylic acid. Okay, with the anion being called a carboxylate ion. And this is just hydrogen ions, or later on it is called a proton. Okay, so just remember, when carboxylic acids are behaving as an acid, what happens? The hydrogen on the OH is being released into the solution as H plus. So you are left with the rest of the molecule, but as an anion. And we call that a carboxylate ion. But specifically, this is an ethanoate ion because there are two carbons. Okay, so you can imagine, depending on what is attached here or how long your chain is, it doesn't matter, because we're only interested in the COOH part of the molecule. And frankly speaking, it's just the hydrogen being lost or being broken down as H plus. Okay, so this is how carboxylic acids behave as an acid. And this is important because you will need this for later when we look at the reaction of carboxylic acids. If you want to copy this down, you may pause the video now. Okay, so this is basically what I was talking about. Oh, there's one thing that I forgot to add to this is, do I have space? Okay, so we say that, again, this may not mean anything to you right now because you've not learned equilibrium, but just add on equilibrium position lies to the left because concentration of H plus is smaller than concentration of CH3COOH. Okay, so I will not explain this further because even if I explain it, it may sound familiar to you, but I'll revisit that part when we look at topic 7 later on. Okay. Right. If you want to copy this down, you can pause here. Okay, moving on. So that's just that. Now we look at the formation of carboxylic acids. You've seen a few examples that shows the formation of carboxylic acids. So this is the learning objective, where you form carboxylic acids from the oxidation of primary alcohols and also the oxidation of aldehydes using an oxidizing agent, potassium dichromate, acidified potassium dichromate or acidified potassium manganate, hydrolysis of nitriles with dilute acid. I'm not sure if this was, I think this is probably something new for you. Okay, part B. It's converting your nitriles into a carboxylic acid. Okay, C is hydrolysis of esters. You've not met this officially in AS level, but I think you've seen this before in O level. It's basically just the reverse of esterification. You break down your ester bonds to form your original carboxylic acids and alcohols. Okay, so first we're going to look at the oxidation of primary alcohols. So if you're aiming to produce carboxylic acid, you don't have to worry about your setup. Okay, carboxylic acid is the final product of the oxidation of your primary alcohol. So remember, when primary alcohol is partially oxidized, it turns into aldehyde. If you continue to oxidize the aldehyde further, then you will get carboxylic acid. So in this example, you have an ethanol to be oxidized using the oxidizing agent. Either you use acidified potassium dichromate or acidified potassium manganate. By the way, when you answer questions asking for oxidizing agent, you have to mention acidified. You have to mention H+ somewhere, or you mention sulfuric acid somewhere, okay? You can't just write down potassium dichromate. That doesn't work. That's an incomplete reagent, okay? And then you heat it under reflux, as I said, because we're not collecting aldehyde, so we don't need a specific distillation setup, okay? When you oxidize ethanol, again, this is nothing new. It forms a carboxylic acid. Just highlight the functional group so that you know that's the only thing that's changed. Everything else stays the same. You still have the CH3, and now you have a COOH. Okay, so remember, the green highlighted carbon is the one that's being changed from an alcohol into a carboxylic acid. Okay, the balance equation is plus H2O, and you need 2 oxygen to balance the equation. The square bracket O is your oxidizing agent, either one, whichever you want to use. Okay, so you have a new functional group, which is COOH, or a carboxylic acid, and this is only achievable with primary alcohol. Okay, so make sure you highlight only primary alcohol can give you a carboxylic acid. In this case, we call it an ethanoic acid, which is a carboxylic acid. Okay, if you want to pause here, you can pause it now. Moving on to the, oh, we haven't moved on yet. Don't forget, when you use this oxidizing agents, you should expect to see color change. When you use dichromate, you will see orange to green. When you use acidified potassium manganate, you will see purple to colorless. The explanation is here. I've already mentioned, when the oxidizing agent oxidizes alcohol to carboxylic acid, the oxidizing agent itself gets reduced. So you can copy this down. It's worth knowing the explanation. It's worth knowing why the color is changed, which ions are in charge of the colors that we observe. Okay, so please copy this down. I know you don't have much space, but try to write down as small as possible. Okay, moving on. Next is oxidation of aldehydes. Again, you don't need special setup for this. You just heat them, choose either one of the oxidizing agent, and then you just see your aldehyde, which is C double bond OH, being oxidized to carboxylic acid, which is COOH. Okay, so you go from a propanol to a propanoic acid. And this propanol must have come from a primary alcohol as well. It's impossible to get an aldehyde from a secondary alcohol. Okay, if you don't remember this, revisit topic 16 regarding the oxidation of alcohols. Okay, this is just a recap. Moving on to the next reaction that produces carboxylic acid is the hydrolysis of nitriles. I don't know if you remember where you produce nitrile, but nitriles is when you have CN. I'll show you. CH3, CH2, C triple bond N. Okay, not sure if you can see that, but this is nitriles. When you have C triple bond, and how do you get nitriles is from halogenoalkanes. You react it with a cyanide, either a sodium cyanide or potassium cyanide in ethanol, then you get this nitrile. So that's in topic 15 for you. It's under the nucleophilic substitution reaction. Okay, so now nitriles are useful in a way that it adds on one carbon to your molecule. Okay, the carbon comes from the cyanide ions. Once it's added to your starting molecule, then you have an additional carbon. So we can convert this nitrile into a carboxylic acid because usually there's more uses for carboxylic acid. Okay, and then you can transform the carboxylic acid into the alcohol that you want, and then you transform it into an alkene, and then you transform it to an alkane. So the possibilities are endless if you convert it to the carboxylic acid. Okay, so carboxylic acids can be prepared from the hydrolysis of nitrile. The hydrolysis of nitriles means we are breaking nitriles in the presence of water. Okay, so we're breaking this bond. All right, you will see later. Either using acid hydrolysis or alkali hydrolysis followed by acidification. So if you use acid, you just add acid, you get your carboxylic acid. If you use alkali, there's an additional step called the acidification. So I'll talk about that shortly. Hydrolysis by dilute acids results in the formation of a carboxylic acid and ammonium salt. Okay, so don't worry about the ammonium salt. The most important thing that I want you to spot is that your CN, which is your nitrile, and this is called a propane nitrile because of the number of carbon, 1, 2, and 3 carbon. So it's a propane nitrile. You have water because it's hydrolysis, it's breaking of bond in the presence of water, and you have the acid. Okay, so that's just to support your hydrolysis. And then look what happens to your CN group. It turns into a COOH. Okay, so as easy as that. The other product that you're forming is what we call an ammonium chloride. You have met ammonium chloride actually in topic 3, where we talk about the coordinate or dative covalent bond. Okay, so ammonium chloride is actually an ionic molecule made up of ammonium ions, NH4 plus, and chloride ion, Cl minus. Okay, so again, it doesn't matter what type of carboxylic acid, it doesn't matter what type of nitriles you use, whether it's a branch, whether it's a straight chain, because this part of the molecule does not get changed. It stays unchanged. The only thing that's changing is the cyano group, or we call it the nitrile group, to be changed into a carboxylic acid, COOH group. Okay, so you just need to heat this experiment in the presence of water, and also in the presence of acid using water. That's why it's called hydrolysis. Next, hydrolysis is the base hydrolysis. Is it the same? Oh, okay, it's the same, right? Basically, this is the diagram that you have in your notes. So we say that the CN group at the end of the hydrocarbon chain is converted into a COOH. So the rest of the molecule stays unchanged. Okay, so if you want to copy this down, you may copy it. Okay, you can pause it here. Okay, next is the base hydrolysis of nitrile, or the alkali hydrolysis of nitriles. So there's an extra step with alkali. Why? Just to remind you, carboxylic acid is an acid. Okay, and then in the presence of alkali, remember, acid will react with alkali. Okay, acid will react with the base. Okay, right. Hydrolysis by dilute alkali results in the formation of a sodium carboxylate. Now remember, I mentioned carboxylate just now earlier on, when carboxylic acid reacts as an acid, it dissociates into H plus and a carboxylate ion. Okay, so there is a connection here, and then you form ammonia. So the ammonia is the side product that you have to memorize. Okay, acidification is required to change the carboxylate ion into a carboxylic acid. Okay, so the reagents you need here is again, water, since it's called hydrolysis, and you just need an alkali, a base, to support this reaction. And the easiest base we use is sodium hydroxide. It's easy because it's soluble, so it will mix well in water, okay? Because not all hydroxides will be soluble in water, which is what you will learn later on, okay? So what happens if we just ignore this part first? Okay, so I want you all to ignore that part first and just focus on this top part. Okay, so we have again a propane nitrile, and as I said, during hydrolysis of nitrile, we're only going to change the C triple bond and bond into a COOH. Okay, now why is it that I'm not getting a COOH? The reason is because, hint, COOH, okay, I'll just draw this, OOH, is an acid. In the reaction mixture, there is a base. So when acid reacts with base, we get salt. Okay, you cannot separate the product carboxylic acid so that it doesn't touch the sodium hydroxide. You can't help it. Okay, so what happens is that the moment you form carboxylic acid, that carboxylic acid will immediately react with sodium hydroxide to form what we called a salt called the sodium propanoate. Okay, the propanoate comes from the 3 carbon, 1, 2, 3, propanoate. So this is an example of a carboxylate salt. Okay, the other product is the ammonia. Now, if you are interested in carboxylic acid and you're not interested in the salt, there's no problem, no need to panic. Okay, you just add acid to your sodium propanoate. What happens if you add H plus? That H plus will kick the sodium ion out so that H plus combine with the COO minus to form the carboxylic acid. Okay, so there's an extra step with alkali hydrolysis, right? Acidification you can use dilute HCl, for example. Okay, so this first part, the condition, that means the condition of the alkali hydrolysis is first sodium hydroxide aqueous, which is water, and then you heat it. Okay, so that's the first part of the reaction. If you want to produce carboxylic acid, you cannot just stop at the first part because all you will get is a salt. The second reagent you need is dilute HCl. Okay, it is important that you number them 1 and 2 and you don't mix them all together. If you mix them together, sodium hydroxide and HCl, what happens? They will react with each other, and this other reaction probably will not happen. Okay, so that it's important for you to separate your first reagent to add in to form your salt, and then only you throw in your second reagent for the acidification process. Now, if I were given a choice to do the hydrolysis of nitriles, to choose between acid and base hydrolysis, I would definitely choose acid because acid only involves one step. Okay, whereas base hydrolysis, you have 2 steps. First is the hydrolysis, and then it's the acidification. Okay, so you try to avoid reactions that have more than one step. Okay, so that's how you form carboxylic acid from nitriles. Okay, the last reaction for the production of a carboxylic acid is the hydrolysis of ester. Okay, so hydrolysis, same thing, we are breaking down the ester bond. Okay, it's the opposite reaction of esterification. So esters can be hydrolyzed and split up by either heating with acid or heating with base sodium hydroxide. Okay, hydrolysis by dilute acid is a reversible reaction and an equilibrium is established. So I don't want to talk about equilibrium just yet. So this is what happens. Okay, okay, so I will draw it for you. Since the equation is given to you, I will show you what happens during hydrolysis. Okay, so if I have an ethyl propanoate, which you already have under acid hydrolysis, right? So this is what happens. I will try to just focus on the ester bond, COCH2 CH3. Okay, so this is our ethyl propanoate. I will not talk about naming it today. COOC. Whenever you see the COOC, it is an ester functional group. Do not get confused. This is not functional. This is not carboxylic acid. This is not ketone. This is ester. Okay. So for ester, the bond is being broken where the bond was made. I don't know if you still remember the esterification process, but the bond being broken is at the C single bond O. And since this is a reversible reaction, we often show it by drawing a reversible arrow. Don't forget your other reagent, which is water, okay, in the presence of an acid. That's why we call it acid hydrolysis. Hydrolysis, again, you need water to break the bond, right? So you form two products. The first one is the part that belongs to carboxylic acid, which is the one on the left. Whoever that is directly attached to the C double bond O, that means it came from the carboxylic acid. Okay, the one that is singly bonded to an oxygen comes from alcohol plus HO CH2CH3. So the hydrolysis of esters give result to the formation of two new functional group, which is COOH and OH, which is an alcohol. Okay, so this is a carboxylic acid called 1,2,3 propanoic. And this is an alcohol. Maybe I'll use different color. This is an alcohol called the ethanol. Okay. The reversible arrow is to show you that the reaction is reversible. Okay, so this reaction is the reverse of an esterification or ester formation in which you produce carboxylic acid and alcohol. Right? If you want to copy this down, you can pause the video here. Okay, so you can add this to your notes. This reaction is reversible. Oh, you have it already. This reaction is reversible and does not give a good yield of the products, even though it's straightforward from ester to give you acid and alcohol. But the only problem is the yield. It doesn't give you a big number of products. Okay. Next is the base or alkali hydrolysis. Now you notice that the arrow is a single headed arrow. Okay, so this shows that the reaction goes to completion. Okay, so there's no forward and then going back to reverse. It only goes from reaction to product. So in terms of yield, this second method is better. Okay, now there's a difference in product that you get if you use base. So the same problem we encounter if we use base hydrolysis for nitriles. Okay, the problem is because the base will react with your carboxylic acid. So that's the problem. Okay, right, so let's have a look. First, we look at methyl propanoate. Okay, so I am just, again, I will only focus on the ester bond, COCH3. Okay, and then we have sodium hydroxide, right? Same thing, I will highlight the ester bond, COOC. This part on the left is attached to the C double bond O, so that's your carboxylic acid part. And the one on the right is your alcohol part because it is attached to a single bond oxygen. Okay, so same place that we are breaking, nothing too different from the acid hydrolysis. The only difference is in the product. Okay, well, one of the products. So we get CH3, CH2, C double bond O, OH, or that's what we think. Okay, just keep in view about this, right? And the other one is an alcohol, HO, CH3. So this is an alcohol called the methanol because there's only one. Okay. Now, the problem with this is that the moment you form an acid, in the reaction mixture, there is a base. The acid would react with the base in such a way that it will lose its H plus. It becomes an anion, a carboxylate, which is called 1, 2, 3 carbons, propanoate. Okay, and the counter ion is just a sodium. So this is called a salt, carboxylate salt. Which is specifically sodium propanoate. Okay, so if you are wondering why there is no acid, it's because the acid reacts with the sodium hydroxide. Okay, now what if you're not interested in the salt? You want to convert it into the original acid. The same way you have done it for base hydrolysis of nitrile. We do the second step, which is called the acidification. And for acidification, you just use any acid, use a dilute hydrochloric acid, and your salt will be turned or converted into acid just like that. What happens is because the hydrogen ions from the HCl will be picked up by the propanoate ion and the sodium ion will be kicked out. Okay, so that's why you get a propanoic acid in 2 steps. The first step is the hydrolysis step. The second step is the acidification step. All right. Again, when it comes to writing down the reagents and conditions, I would suggest you to always number them, okay, separate them. First, you use sodium hydroxide aqueous, heat. Secondly, you add dilute hydrochloric acid. Do not write it like this, huh? Okay, so what you must not do is this. You've got sodium hydroxide, you've got dilute hydrochloric acid. They will react. Sodium hydroxide plus hydrochloric acid, it reacts into sodium chloride. So this reaction will not happen. Okay, so you want to separate the base and the acid, and you add it one at a time. First, you add aqueous sodium hydroxide with heat, and then dilute hydrochloric acid. Okay, let's see, is there anything that I want to add on? I think that should be it. Okay, so we've got a few more to go, but I wouldn't cram everything in this lesson. Okay, as usual, after you've watched this video, please make sure you answer the post-test questions and forms, you can find the link in the description box. And also you have an extra task. Okay, your additional task is to do exercise 17.1. Okay, so please refer to the document, your task for exercise 17.1 on Saturday. Okay, all right, assalamu alaikum and thank you.